Hello, I'm Norman Wildberger, and today we're going to continue with our discussion of 2x2 matrices and their applications. It's a very rich area of linear algebra because it's an arithmetic which is better and more beautiful than the usual arithmetic and has interesting applications to two-dimensional transformations. Today we're going to talk about the connections between matrices and linear transformations. We're going to talk a little bit about rotations, and we derive some interesting trig identities just by talking about matrix arithmetic. We're going to look at more general reflections. We're going to look at combining rotations and reflections, and we're going to look at applications a little bit to calculus too. So let me remind you that our basic setup is that we have a 2x2 matrix A, B, C, D, and it multiplies a vector, a column vector xy, according to this definition. So let's just review that. It's a very fundamental formula. To get the first entry, it's A times x plus B times y. We go along the first row of the matrix on the left. And to get the second entry, cx plus dy, we take this product plus this product. We go along the second row. And our notation for this, if that's the matrix capital A, and that's the vector v, and that vector is v prime, say, so A times v equals v prime. Now we can use this matrix multiplication on a vector to define a mapping, or perhaps it's called a function or a transformation. Let's say t of v. So we're thinking of this as an input-output situation. We can visualize what's going on here by inputting v, outputting this v prime, which is A times v. So that defines a transformation or a function, which we're going to call t. And it sends vectors to vectors. And an exercise that I left you with last time is to convince yourself that this transformation is in fact a linear transformation. It has a particular properties that, first of all, t of lambda v equals lambda t of v for any scalar lambda, any vector v. And if you apply t to a sum of two vectors, you get the sum of the two actions on v and w. So our first order of business is to prove this very useful law. We want our argument to be a general one. So we start by letting A be the matrix A, B, C, D with general entries. By letting V be the vector xy with general entries, and W being the vector with, say, entries T and U. So we're just introducing letters here to stand for these arbitrary entries. And now let's look at the first line, T of lambda V. By definition, what does T do to lambda V? It multiplies it on the left by the matrix A. And A times lambda V, there's the matrix A, and lambda times this vector V is the vector lambda x, lambda y. That's how we multiply a vector by a scalar. And now we need to know how to multiply these two things, which I told you on the previous slide. It's A times this plus B times this. And the second entry, C times this plus D times this. On the other hand, if we look at lambda times T of V, well, there's lambda. T of V is the effect of multiplying A by V. So that's AX plus BY, CX plus DY. And if you multiply this by lambda, it simply means multiplying each of these by lambda. And then you see, if you compare these two things, if we multiply this by lambda, we get A lambda x, B lambda y. That's the same as up here. If we multiply this by lambda, we get C times lambda times x plus D lambda y. That's the same as there. So we conclude that T of lambda v equals lambda times T of v. And the second property is T of v plus w should be T of v plus T of w. So let's compute those separately. T of v plus w, by definition, that's A times v plus w. What's v plus w? Well, it's just the sum of those two vectors. So there it is there, x plus t, y plus u. We just add the components. We have to multiply by the matrix A. So what do we get? Well, it's A times this plus B times this. It's all in one line. And below it, C times this plus D times this. Over here, T of v plus T of w, that's A times v plus A times w. Here's A times v, here's A times w. When we add these two, we just add all the components. So we get 4 there and these 4 there. And then we compare this, and we see that they're the same. And so T of V plus W equals T of V plus T of W. And as I mentioned last time, knowing that a transformation T is linear allows us to conclude this important little rule. That if we apply T to a combination of two vectors E1 and E2, say x E1 plus y E2, then that's equal to x times T of E1 plus y times T of E2. So that's a combination of both of the properties of a linear transformation. So let's have a look at an example. This shows a transformation T which does something to the vectors E1 and E2 very explicitly. It sends E1 to this vector T of E1 right here, and it sends this vector E2 to this vector T of E2. So I've used separate pictures here instead of superimposing them so that it doesn't get too cluttered. But these are really the same copies. There's the origin there, there's the origin there, and our scale is the same. Now, our setup here is that the vector E1 that we've chosen and the vector E2 are our standard basis vectors, which we call 1, 0 and 0, 1. Over here, with the same reference frame, this T of E1 is 3 over and up 1, so it's the vector that we would be calling 3, 1. And T of E2, this vector is minus 1 in this direction, up 2 in that direction, so it's the vector minus 1, 2. So we could describe this transformation by saying that it sends the vector 1, 0 to the vector 3, 1, and it sends the vector 0, 1 to the vector minus 1, 2. Now this property here allows us to visualize this transformation in a very nice way. Okay? So instead of concentrating on what individual vectors go to, it's nice to think about what happens to the entire grid. Okay? This entire family of green lines that are equally spaced in both directions, separated by these two vectors E1, E2. This family of lines gets mapped to the family of lines that are over here. So how does that work? So this line, that's a multiple of E1, well, that'll get sent to that. This line gets sent to this. But because of this linear property, these lines here are going to go to these lines here. And these lines here get sent to these lines and so on. So the entire grid gets, in some sense, a little bit rotated, a little bit distorted, a little bit enlarged, and gives us a new grid over here. So for example, suppose we looked at this particular vector, the vector that's over here, coordinates 1, 2, that we're calling V. Then without any calculation, we know that that vector has got to go to, because this is 1 times E1 and this is 2 times E2, it's got to go to 1 times T of E1 plus 2 times T of E2. In other words, the vector which is up here. So once we know T of E1, once we know T of E2, then we can calculate the image of any other vector very simply just by using this little identity. All right, so that vector is going to get sent to this vector here. Another example, this vector U here, which is minus 1 E1 plus minus 1 E2, that's going to get sent to minus T of E1 plus minus T of E2. In other words, the sum of these two vectors, which is down here. Or if you like, it just goes to corresponding points on the grid plane. That point on the grid plane corresponds to that one over there. Now, an interesting feature of this transformation, it preserves this grid in a very nice way, moves it around, distorts it, changes its area. The area dilation factor going from this grid to this one is calculated by finding the area of this basic parallelogram in terms of this one. And that's a calculation that we've done already. So here is a vector 3, 1. Here's the vector minus 1, 2. What's the area of that parallelogram? Well, that's an AD minus BC formula where there's one column, there's another one. So there's AD minus BC. So it's 6 minus -1, that's 7. So the determinant, or the delta function in this case, is 7, and that's telling us that this linear transformation is expanding or dilating areas by a factor of 7. This area gets sent to that area, which is 7 times as much. This area here gets sent to that area, which is 7 times as much. And the area of any configuration over here gets sent to something over here, which is 7 times as much. So a natural question that you might have at this point is, suppose that we were given a linear transformation in terms of a matrix. How do we find out what these basis vectors go to? That's a good question, and there's a very nice and pleasant and important answer. So suppose that our transformation is given by multiplication by a matrix A, and suppose it's that matrix right there, A, B, C, D. Here are our standard basis vectors, what we're calling E1, coordinates 1, 0, and E2 with coordinates 0, 1. How do you find what T of E1 is? Well, you just take the matrix and you multiply it by the vector 1, 0. And how does that matrix multiplication go? Well, it's A times 1 plus 0 times B. So that's just A. And then the next one is C times 1 plus D times 0. That's just C. So we're just picking out the first column. That's what T of E1 is. The first column of the matrix A. And T of E2, there's A, there's 0, 1, that's our vector E2. The multiplication now looks like 0 plus B, that's B, and 0 plus D, that's D. We're getting the second column. Conclusion, T of E1 and T of E2 are the columns of A. So suppose that our transformation is that T of V is that matrix, 3 minus 1, 1, 2, times that vector V. Then T of E1 is 3, 1, because that's the first column. And T of E2 is minus 1, 2, that's the second column. So this transformation here is the one that we were talking about that had a delta of 7. Here's another question. What is the linear transformation T, sending this vector 1, 0 to 5, 3, and the vector 0, 1 to minus 4, 11? Well, now we've given the information the other way around. Now we know what T of E1 is. It's that. And there's T of E2 there. So our transformation is a multiplication by a matrix whose first column is 5, 3, because that's T of E1, and whose second column is minus 4, 11, because that's T of E2. And what happens when we multiply this vector by that matrix? We get 5x minus 4y and 3x plus 11y. So that's the linear transformation that takes the vector xy and sends it to this vector. That vector has the property that this basis vector goes there and this basis vector goes there. By the way, I end my examples often with a little red diamond. All right, same question as the previous one, but now we're told that we have a linear transformation that sends the vector 1, 0 to the vector minus 2, 3, and it sends the vector 1, 1 to the vector 5, 1. It's not exactly the same because we're not told what 0, 1 gets sent to, only what 1, 1 gets sent to. So in order to cook up the matrix in a way that we did up here, we need to know what 1, 0 gets sent to and what 0, 1 gets sent to. So how do we deduce that? Well, we make the observation that the vector 0, 1 is actually the difference between these two vectors. If you take this vector and you subtract that vector, then you get the vector 0, 1. But T of a difference is T of the first vector minus T of the second vector. That's the linear transformation property applied twice essentially. You're using the additivity and also the fact that the minus 1 scalar comes out. But T of 1, 1 we're told is 5, 1, and T of 1, 0 we're told is minus 2, 3. So T of 0, 1 has got to be the difference between these two, which is 7 minus 2. So now we can cook up the matrix because we know what T of E1 is, and now we know what T of E2 is. So to finish that example, we can conclude that T of a general vector xy is this matrix multiplied by xy, obtained by taking the image of T of E1 there, and the image T of E2 there. When we multiply that out, that's minus 2x plus 7y and 3x minus 2y. That's the transformation that has the properties we were asked. All right, now let's apply our understanding of linear transformations and their connections with matrices to the very important subject of rotations. Okay. We want to understand rotations in the plane. And a good starting point is to start with the unit circle. Let's review a few basic things about the unit circle. So we're using our standard x and y coordinate system. It's now a little bit expanded, so there's 1 unit. So that our unit circle right there is a little bit bigger than usual. And I remind you that it has equation x squared plus y squared equals 1. All the points on here have x squared plus y squared equals 1. Okay, what's a typical point on here? Well, the usual framework for thinking about the unit circle is in terms of angles. It's not actually the best way of thinking, but let's stick with angles for a little while. So if there's an angle theta, say, usually measured from the x-axis and usually measured so that this is the positive orientation. So angles in this direction are positive, angles in this direction are negative. Then this vector here is given by the circular functions cosine and sine, because cosine represents the x component and sine represents the y component of an angle theta. There's no factor because this is a unit circle, so the radius in this case is 1. So that's our name for this vector here. We're going to be interested in rotation by an angle theta. And this vector is obviously important because that's going to be the image of this basis vector E1 under rotation by theta. T of E1 is going to be that one there. We won't use T, we might use rho sub theta to represent our rotation. Now, if we know that rotation there, what happens to E2? Well, this rotation has got to send these two perpendicular vectors to another pair of perpendicular vectors. So this vector here has got to be 90-degree rotation from this one. So in fact it turns out to be minus sine theta cos theta. And you could get that by applying what we did already in a previous video. We analyzed rotation by 90 degrees. Remember there I explained that if you had rotation by 90 degrees, it was like multiplying by the matrix 0, minus 1, 1, 0. And what it did to a vector xy, it sent it to minus yx. Do you remember that? So if we apply that to this, if that's xy, then this is minus yx. We're just exactly applying a rotation of 90 degrees to get from this point or vector to this point or vector. That's good now because now we understand where the basis vector E1 goes under this rotation and where the basis vector E2 goes under the rotation. And that's all we need to know to be able to write down the matrix for the rotation. And once we've written down the matrix for the rotation, we know everything about it. Okay, so what is that matrix? Well, it's just the matrix whose first column is what happens to E1. There's T of E1. And whose second column is what happens to E2. There's T of E2 down there. So rotation by an angle theta acting on a vector V is simply taking this matrix and multiplying it by the column vector V. So this is a very important form, and when you see that you should recognize rotation, and given an angle theta it'd be very good if you sort of remember this formula. It's an important formula. It's the formula for the rotation in the plane by an angle theta. Let's look at some specific examples. Here again is the unit circle with vector 1, 0 there and 0, 1 there. And I've drawn a few other important points. These points are very familiar to high school students and college students because they're the ones that are used for most tests and examples. We're talking about 45 degrees and 45 degrees in this other direction, it's 135 degrees. And we're talking about 30 degrees and 60 degrees. And corresponding reflections on this side, that'd be 120 and 150. There's really 4 points here in this first quadrant, these 4, and then those 4 points are repeated by rotating by a half turn to the other 4 quadrants. So I've given the labels for these points in these quadrants here. To get the other ones, it's just a question of reflecting and putting some minus signs. So here is 30 degrees, and the point on the unit circle, which is at an angle of 30 degrees, has the coordinates root 3 on 2 and 1/2. Square root of 3 is a little bit bigger than 1, so it's got a bit bigger x component than y component. For the 45 degrees, this is this black one here, the x and y values are the same. They're both root 2 over 2. And for 60 degrees, we're getting exactly the same thing as here, but with the x and y interchanged. So now the x coordinate is 1/2, and the y coordinate is root 3 on 2. Okay, it's very important for high school students and college students to memorize these formulas because it really contains the values for cosine and sine of 30 degrees and 60 degrees and so on. So another way of saying it is that the cosine of 30 degrees, which is the x coordinate, is root 3 on 2. And the cosine of 60 degrees is 1/2. And then there are these other variants obtained by taking these 4 points and just sort of reflecting them around. So for example, this point here, which is the reflection of this one in this line here, is obtained by just taking these coordinates and replacing the x coordinate with its negative. So you can just reflect in the same way to get those points and those points and those points also if you want. Now once we have the point or the vector on the unit circle, we can write down the rotation matrix. We gave the general formula on the previous slide. So for example, row of 60 degrees. The rotation of 60 degrees has a matrix, this one here, obtained by taking the point 1/2 root 3 on 2. There's the first column, and flipping it over and putting a minus sign, minus root 3 on 2 and 1/2 for the second column. Rotation by 30 degrees has this as its first column, and then the other one is obtained by putting that one up there with a minus sign and putting that one there. 45 degrees, that column, plus its flip. And I've given you this one here also. A rotation of 150 degrees would be that column there goes in the first column, and then flip it around, put a minus sign, minus 1/2 minus root 3 on 2. So each of these represents a rotation by the corresponding angle. And it gives us a very explicit way to evaluate what these rotations do to arbitrary vectors in the plane. So for example, suppose you wanted to know what rotation by 30 degrees does to the vector 7, 4. What would you do? You would take the matrix for that rotation, which is this one here, and you would simply multiply it by the column vector 7, 4. And that answer, that column vector that you get, would be the effect of rotating 7, 4 by 30 degrees. So it's an attractive picture, but it's really not as attractive as people imagine, because unfortunately these are pretty well the only values that are known explicitly to undergraduates. Although there's billions and zillions of points on the unit circle, these particular ones get used over and over and over again. It's a bit unfortunate, and there is an alternate framework that I will tell you about in a little while. But let's first have a look at an interesting application of these rotations matrices to some trig identities. Alright, so there I've repeated, there's our matrix for rotation by an angle theta, for the linear transformation rho sub theta. We're calling it A. Suppose you rotated by theta, and then you rotated by theta again. How would you incorporate that using the matrix idea? Well, you would take your vector v and you would rotating by theta is multiplying by the matrix A. So you multiply by the matrix A. And then you have to multiply by the matrix A again, because that's what you do when you rotate the second time. So altogether you're multiplying by A and then you're multiplying by A again. So you're really multiplying by A squared. And it's interesting to calculate what A squared is, because it represents the rotation by 2 theta. So to make it a little bit shorter, instead of writing cos theta, I'll just write c of theta. Instead of writing sine theta, I'll just write s of theta. So there's the matrix A repeated, there's the matrix A repeated again, and now I'm just multiplying those two matrices. So this times this, that's cos squared theta, minus sine squared theta, that's the top entry. And down here, cos times sine plus cos times sine. So that's 2 times cos sine. The second column, to multiply this by this matrix. So cos times minus sine plus minus sine times cos. That's minus 2 cos theta sine theta. And this entry here is minus sine squared plus cos squared. Cos squared theta minus sine squared theta. That's another matrix in exactly the same kind of form, and it is in fact the matrix whose entries have to be cos 2 theta and sine 2 theta minus sine 2 theta cos 2 theta, because that also is the matrix for rotation by 2 theta. So we have two different formulas for the same thing. That's good. It means we can compare them and extract some information. When we compare this to this, we see that cosine of 2 theta has to be cos squared theta minus sine squared theta. And sine 2 theta has to be 2 times cos theta sine theta. And we've obtained that by the arithmetic of 2 by 2 matrix multiplication. And an excellent exercise is to extend this to find formulas for cos 3 theta and sine 3 theta in terms of cos theta and sine theta. So what you have to do is you have to multiply this a squared by another a. So you're really looking at a cubed and seeing what the entries of that are. When we discuss rotations, it's useful to realize that there are 2 points of view to looking at the unit circle. The cosine theta, sine theta parameterization is actually a relatively modern one, and there's a much older parameterization that goes back to the Pythagoreans and to Euclid. It involves parameterization by 2 rational functions, that is, just ratios of polynomials. The function c of h defined to be 1 minus h squared over 1 plus h squared, and the function capital S of h equals 2h over 1 plus h squared. If we combine these 2 functions into a vector like that and call that vector e of h, then we get a parameterization of the unit circle, because this squared plus this squared always equals 1. That's a basic identity that goes back to Euclid. And the significance or the meaning of it is that if we look at the point on the y-axis, which is of height h, and we join that point to this point minus 1, 0 here, then the other intersection point with the unit circle is exactly this point. A derivation of this fact is described in one of my videos in the Wild Trig series called Rational Parameterization of a Circle. As an example, suppose that h were exactly halfway here, so h is equal to 1/2. If you plug 1/2 into here, you get e of h equals 3/5, 4/5, which corresponds to a right triangle with sides 3, 4, and 5. This is a way of getting points which are actually precisely on the circle, whereas the cos theta, sine theta formulation of things only gives you points which are approximately on the circle, unless you restrict to that handful of points that we discussed earlier. So for many purposes, this kind of parameterization is preferable. If we're talking about rotations, we can use the fact that we now have a unit vector in this form to write down the corresponding rotation matrix. I'll remind you what we do is we just take that unit vector and put it down the first column of our matrix, and then the second column is obtained by interchanging and putting a minus sign there. That makes that a rotation matrix, and that's an alternate framework. Instead of using cos theta, sine theta, minus sine theta, cos theta, this is another way of thinking about what a rotation is. 2 remarks. First of all, that this point here has a sort of a special role in this framework. It actually corresponds to the parameter h equals infinity. When h, you have to move h all the way up there or all the way down there to get at this point here. The second thing is, in a very nice little exercise, that when you compute how matrices like this multiply, you get the following relation, that BH prime times BH equals BH double prime, when H prime is given by this formula. So this replaces the addition of angles. It's a little bit more complicated. H double prime is H plus H prime divided by 1 minus H prime. Okay. That's an exercise that you can do purely using the algebra, polynomial rational algebra of these two functions. So we're going to talk a little bit more about this approach to polar coordinates a little bit later on, but I just want to alert you to the fact that there's actually another way of thinking about the parameterization of the unit circle, and to get you thinking about the idea that in many ways it's better. Now I'd like to show you how to deal with the reflection in a line where the line is not quite as simple as simply being 45 degrees or the coordinate axes. Let's look at this line here, this line L, which goes through the vector 1, 2. We're interested in the reflection in that line, let's call it sigma L, and describing it precisely in a matrix kind of formulation. To do that, let's introduce this vector v1 with coordinates 1, 2 that lies in the line. It's a direction vector for the line. And a vector perpendicular or normal to the line, which is obtained by rotating this one by 90 degrees or a half turn. That's minus 2, 1. So there's the vector minus 2, 1, which is perpendicular to the line. These two vectors are useful because the reflection in the line treats them very simply. If we reflect in this line, then this vector v1 is unchanged. So sigma L of v1 is v1. While this vector here is reflected in that line to give negative itself. So sigma L of v2 is minus v2. Now to write down a matrix for this transformation, we need to know what happens to E1 and E2, our standard basis vectors, when we reflect them. Now we could try to do that directly, but a very interesting approach is to use the fact that we already know what happens to V1 and V2. And the idea is that we're going to express E1 and E2 in terms of V1 and V2, and then use that earlier fact. What we do know at this point is that V1 is a combination of E1 and E2 because it's the vector 1, 2, so it's E1 plus 2E2. And V2, the minus 2, 1, is minus 2E1 plus E2. So how would we solve this little system for E1 and E2? Well, that's a familiar problem that we've solved several times. That's our basic problem for linear algebra, how to invert a change of variables. Except here we don't have variables x and y, we have vectors E1 and E2 and V1 and V2. But nevertheless, the algebra is exactly the same. Let me remind you what we did. We wrote down another formula for E1 and E2 which involves some new coefficients obtained by dividing first of all by a determinant. The determinant is 1 times 1 minus 2 times minus 2, which is 5. And the other coefficients are obtained by interchanging these two diagonal coefficients. Well, they're both 1, so we interchange, it doesn't do anything. And multiplying the off-diagonal coefficients by minus 1, giving us minus 2 and 2. So this is the expression of E1 and E2 in terms of V1 and V2. And once we have that, then calculating what t does to E1 and E2 is simply a matter of using the linear property of t and the fact that we know what it does to V1 and V2. So, for example, t of E1 is, well, it's going to be 1/5 of t of V1 minus 2/5 t of V2. But t of V1 is V1 and t of V2 is minus V2, so we get 1/5 V1 plus 2 V2. And what is this? Well, V1 is that vector, V2 is that vector. When we take this combination, we're getting this plus 2 times that. So there's a 1 minus 4, that's minus 3, and a 2 plus 2, that's 4. When we divide by 5, we get minus 3/5, 4/5. Exactly the same way, we apply t to this. It's 2/5 t of V1, which is V1, plus 1/5 t of V2, which is minus V2. And then this expression here, 2 times this minus this, becomes 2 minus minus 2, that's 4. And 2 times 2 minus 1 is 3. So we get 4/5, 3/5. So this is what we wanted. These are the images of E1 and E2 under the transformation. So the vector E1 gets sent to the vector minus 3/5, 4/5. So it gets sent to a vector up like there. And the vector e2 gets sent to 4/5, 3/5, that's 4/5, 3/5, somewhere like that. And that pictorially makes sense. And now we can write down the matrix for this linear transformation. Here it is right here. There's the matrix for the reflection in the line L. The first column is the image of E1 under the transformation. This second column, the image of E2. And now let's turn to another application of our matrices, the idea of composing linear transformations, of being able to compute what happens when we do not just one thing, but several different things in a row. That's called composing. So for example, suppose our first linear transformation, called it T, takes V to A times V. A is some 2 by 2 matrix. And suppose we have another linear transformation, let's call it S, whose action on V is to multiply V by B, another 2 by 2 matrix. Well, we can combine those two, and this is called the composition of T and S. It's denoted by T circle S. And by definition, that means that it's what happens when you take V and you first apply S and then you apply T. So V acted on by S, so S of V, and then that input to T, T of that. And our notation is such that when we read from left to right, it's T and then S and then V, and this is also T and S and V. Even though actually in terms of operations, we're doing this S first and then the T. In terms of our matrices A and B, T circle S of V, what does it do? Well, S multiplies V by B, so there's S of V. And then when we apply T, we multiply by A. So it's V multiplied by B and then multiplied by A. But remember that we defined our matrix multiplication exactly so that this kind of combination was the same as multiplying V by the combination A times B, the product matrix A times B. And that means that this composite linear transformation is itself a linear transformation. It's multiplying by this matrix, this product matrix. So composition of linear transformations corresponds to multiplication of matrices. And that's a very important and natural interpretation of what matrix multiplication is or means. And it's the interpretation that I want you to have. The product of two matrices corresponds to doing one transformation and then doing another transformation after that. So let's look at an example where our first transformation, let's call it T, is rotation by 45 degrees. So for example, that vector E1 gets sent to that vector there. Everything gets rotated by 45 degrees. And the second transformation is reflection in the line L. We're going to choose the same line that we did in the previous example, the line through the vector 1, 2. Now we know the individual matrices for these two transformations. Rotation by 45 degrees has this as its matrix. Root 2 over 2, root 2 over 2, minus root 2 over 2, root 2 over 2. And let's call that matrix A. While reflection in the line L, that's the matrix we just computed, that's this matrix right here, minus 3/5, 4/5, 4/5, 3/5. Let's call that B. So if we're interested in S circle T, say, that's the effect of doing T first and then S. That corresponds to first multiplying by A and then multiplying by B, which is the same as multiplying by BA, because the order has to be preserved. So what is this matrix B times A? This B times this A. Here's our matrix B. Here's our matrix A. We have to multiply them. It's a little bit complicated because the entries have fractions and square roots in them. We can simplify things by taking some common factors out of both matrices. So out of this matrix here, we'll take a common factor of 1/5. So we'll take that 1/5 out front, because remember, 1/5 times a matrix just multiplies each entry by 1/5. So we're not changing anything by bringing that 1/5 out. And what's left is just minus 3, 4, 4, 3. And here we'll take the common factor root 2 over 2 out, leaving just 1, minus 1, 1, 1. The common factor here is root 2 over 10, and multiplying these two matrices now is relatively simple. Minus 3 plus 4 is 1, 4 plus 3 is 7. And here, minus 3 times minus 1, that's 3, plus 4 is 7, and minus 4 plus 3 is minus 1. And what does this kind of matrix look like? Is it a rotation? Is it a reflection? Well, it looks a lot more like this matrix here, because the two diagonal entries are negatives of each other, and the off-diagonal elements are the same. This was a reflection matrix. And this is also a reflection matrix. These columns, in fact, are vectors of length 1, which has to be the case because E1 under rotation and then reflection still is a unit vector, as is E2. And where are these vectors? Well, the first column, 1, 7, divided by its length, 1, 7, that'd be up there somewhere. We scale it so that it's on the unit circle. It's that vector there. That's the first column. So that's the image of E1 under the transformation. And the second column, 7, minus 1, 7 that way, minus 1 that way. We scale that, we get this vector here. That's the image of E2. So we have some transformation that takes E1 to this vector and E2 to this vector, and that's reflection in some line M, which we don't quite know, but it's somewhere in between there. It's actually an interesting problem and an important problem to try to figure out what this line M actually is. In which direction is the line that's halfway? That's also a very important problem in linear algebra that we're going to say more about later on down the road. But you can think about it as a little challenge for you to see if you can figure out where this line M actually is. If we did things in the other order and we did the reflection first and then the rotation, we would have to multiply the matrices in the opposite order. So it would be much the same, except we would get this matrix here, which is also a reflection matrix, and I'll leave it to you to try to figure out where the reflecting line might roughly be. Let's call it N. But in both cases, we're multiplying rotation by a reflection, and we end up getting another reflection. So in this course, we're going to be sticking to linear transformations, and after you get used to them, linear transformations are in some sense a little bit simple, especially in the plane. And you might say they're a little bit limiting because most things that are happening, most kind of transformations in the real world are not necessarily linear. That's true, but there's an important way in which linear transformations have a lot to say even about nonlinear transformations. So let's give an example of a nonlinear transformation just in the plane. So there's our plane starting off with our nice regular pattern of coordinate lines, x and y. And now we have some nonlinear transformation represented by the image of those grid lines, some kind of curved family of lines. So perhaps that line there might go to this line here. Examples of nonlinear transformations are easy to cook up. You just take your vector x, y, and you send them to another vector where the entries are somewhat arbitrary. For example, it could be x squared plus y, x minus y cubed. That would give some nonlinear transformation. Or perhaps x sine y and 1 over x plus log y. You can do basically whatever you want. You're going to get some complicated transformation. The ones we've been studying are very simple, where there's just x's and y's appearing linearly. But what happens is that even a complicated one like this can be approximated by a linear transformation close to a point. So let's say we're looking at this point here, let's call it V0, and its image here, let's call it U0. And suppose we have our magnifying glass and we just concentrate on a small area around that point. And we look at the image of the points near our V0. Where are they going? Well, so here's a magnified picture. We've subdivided our grid into a much finer grid. There's our point V0, and there's some neighboring regular grid lines. and we look at the image of this little thing, this little patch right around here, we can get another patch close to this point here. Represented in the green, perhaps something like this. And what we're going to notice is that if we choose a small enough patch, in other words, a big enough magnifying glass, then the picture of what happens to the lines near V0 is described by a linear transformation. In other words, what's going to happen to this line, these lines over here, is they're going to form a nice regular affine grid situation with lots of little parallelograms. In other words, described by a linear transformation of the kind we've been talking about. So even though globally it's nonlinear, locally it's approximately linear. And this is a very important idea. In fact, it's one of the main ideas of the differential calculus. So let me give you an idea of how this works by looking at a particular example. Let's just arbitrarily choose this nonlinear transformation. So some transformation that sends a vector xy to another vector given by x squared plus yx and 2x squared minus y cubed. And let's look at a particular point. Let's say the point 2, 1. What's the image of 2, 1? Plug it in here, we get 4 plus 2, that's 6. 8 minus 1 is 7. So the image of 2, 1 is 6, 7. And now let's have a look at what this transformation looks like near the point 2, 1. For that, let's call 2, 1 u0, and let's look at a neighboring point. So u0 plus some little incremental vector. And we're going to call that vector dx dy. This notation goes back to Leibniz, who was one of the founders of calculus. And dx is not d times x, it's rather just a small change in x. And dy is just a small change in y. So the dx is alerting us to the fact that these two quantities are very small, like maybe 1,000th, or 1,000,000th, or 1,000,000,000th. And they're so small that we agree that if we square them, then we get a number which is incredibly small, almost invisible. So if you have 1,000,000th, it's pretty small. Let's say you can see 1,000,000th, but if you square it, then you have 1,000,000th times 1,000,000th, that's 1,000,000,000,000th or something. And that's going to be invisible to you. So dx has the property that if you square it, it's essentially 0. And if you cube it, well, then it's even smaller. It's still essentially 0. So we combine u0 plus this little increment. We're talking about the vector 2 plus dx, 1 plus dy. That's a vector near this vector here. And let's have a look at what this transformation does to this nearby vector. Well, we have to plug these values into here. So we get 2 plus dx squared, plus there's the y term, there's the x term. Have to multiply them. And the second coordinate, 2 times the x squared minus the y term cubed. All right, now we can expand this. So it's a bit of arithmetic here. The square of this is square of the first term, 4, plus twice the product, 4dx, plus dx squared. But we've agreed that dx squared is negligible. We can't see that. So let's just not write it down. We'll ignore it. Over here, expanding, 1 times 2 is 2. 1 times dx is dx. 2 times dy is dy. And there's also a dy times dx term. But that's quadratic. That's much smaller than dx or dy, so it's invisible to us. We ignore it. Here, 2 times, well, it's the same thing we had up here, so it's just basically 2 times this, 8 plus 8 dx. And now we have to subtract 1 plus dy cubed. We have to use the binomial theorem to expand a cube. It's 1 cubed, which is 1, plus 3 times this thing squared times that. So 3 times dy. And then the next term is 3 times dy squared. But dy squared, we've agreed, is pretty well 0, so we ignore that. And finally, there's a dy cubed, which is even smaller, and we definitely ignore that. So we've dropped all but the linear terms in dx and dy, and now we get something that's relatively simple. 4 plus 2 is 6, and here we have 5 dx's altogether, plus 2 dy's. And here 8 minus 1 is 7, plus 8 dx's minus 3 dy's. So in the neighborhood of 2, 1, this transformation is taking a nearby vector and sending it to 6, 7, which we know that's where 2, 1 goes, plus some change. So the change dx dy near the point u0 manifests itself in a change of this near 6, 7. And this change is related to this change by a linear transformation. In other words, by a matrix. So the transformation t, acting on the vector 2, 1 plus some small incremental vector, is t of 2, 1 itself plus another vector which is obtained from the incremental vector dx dy by multiplying it by a matrix. The matrix is 5, 2, 8, minus 3. Those are those coefficients that appeared. And this matrix is the derivative of the mapping t at the point u0 equals 2, 1. It expresses how to go from a small change near 2, 1 to a small change near the image. There's a change near 2, 1. There's the corresponding change near 6, 7. That is the derivative. So, derivatives are linear transformations. This is another or a different interpretation of what a derivative is from the first year calculus course, where we think of a derivative as being the slope of a tangent line. Which is the better way of thinking? Probably this way. The linear algebra way is a more general and more powerful and conceptual way of thinking about what the derivative actually is. So mathematics is not just compartmentalized. These various subjects interact, and linear algebra and calculus have a lot to say about each other, especially when you go to higher dimensions. And so that's another good reason why we're studying linear transformations, because it's going to give us a language to talk about calculus in higher dimensions. So we've had a look at some applications of 2 by 2 matrices. Now let's have some exercises. In exercise 7.3, I want you to look at different types of 2 by 2 matrices. We'll talk about diagonal matrices. Those are ones with zeros off the diagonal. Upper triangular matrices where there's a 0 down here. Lower triangular matrices where there's a 0 up here. And I want you to show that each of these families is closed under the matrix operations. In other words, for example, if you took upper triangular matrices, then if you scalar multiply any one of them, or you add any two of them, or you multiply any two of them, you still end up within that family. So we have 3 closed families of 2 by 2 matrices. There are others as well. In exercise 7.4, I want you to explicitly describe the transformations that are associated with a bunch of matrices, just to give you some practice at seeing what matrices actually do in the plane. So here are the matrices, -1, 0, 0, -1, and so on. There's that one, and there's that one. Figure out what they do. Draw some pictures. And you've also got to be able to go the other way around. Given a linear transformation, you want to be able to write down a matrix for it. So this exercise gives you some practice. If we consider t rotation by -120 degrees, s reflection in the line y equals -x, r reflection in the line y equals x, those are 3 transformations. I want you to write down the matrices that represent them. And then following on from that, exercise 7.6, using those values t, s, and r, I want you to describe and determine what happens when you compose various combinations. T circle s, t circle t. You're allowed to compose a transformation by itself. S circle t, s circle r, r circle s. It's a bit of matrix multiplication and interpreting what you're getting. And finally, an example that allows you to play around with this idea of a derivative as a linear transformation. So here's some function which is not linear. Call it t, and I'm asking you to find the derivative of this thing at this particular point, u0. Next time, we are going to address the main problem of linear algebra in the 3 by 3 case. So we're moving up from the 2x2 to the 3x3 case and solving the main problem. So it's going to be a very important lecture. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.